I want to talk about derivatives, first a short video and then a video which is really going to be good for making things a lot easier. In both videos I'm going to talk about this function, x cubed minus 2x squared plus 1, just a good example of a cubic function, has some interesting stuff to it. I've let the computer graph it for me, and then I've drawn in 3 tangent lines, a couple of horizontal ones because those are always good to know about, and then one random one at x equals 2, which we'd like to focus on maybe to start with. Okay, so let's think about what derivatives really tell us. They tell us what happens when we zoom in on a function. And when we zoom in, we see what we usually see, which is this function looks more and more linear. Especially if we really zoomed into here, we could hardly tell the difference between the function and its tangent line. And so it'd be really nice to know the slope of that tangent line. Well, roughly we can estimate it from this graph. You might want to pause a second if you want to estimate it yourself. If we go over 0.1, we go up about 0.4. It looks like right around 4 is the slope of the tangent line. Okay. Well, we'd like to do better than that. I claim that in fact the slope is exactly 4. And I want to show you the quick and dirty way to calculate that. But first, and that's going to be the next video, first I want to remind you of what the usefulness of that is, and the terminology we've just recently learned for that, which is that if we vary x by a small amount dx near x equals why did I say 2? 4. 2. There we go. Near x equals 2, if we walk a little bit to the left or right on x and we measure the height of the graph, then the change in y will be roughly what we call dy. That's the idealized change in the y variable, and that's exactly equal to 4 times dx because the slope is 4. So idealized change in y is 4 times the change in x. Now remember, we really have, if we really wanted the honest to God change in y, we'd call that delta y, and we would not say that's equal to 4 dx. It's approximately equal to 4 dx. But most of the time, very often, we're going to settle for this approximate change, and that's a very nice notation for it. This is the predicted approximate idealized change based on just extrapolating along the tangent line. Okay. So for example, if I increase x by a small amount, 0.05, then it looks like, let's see, how much does it look like y goes up? From about 1 to about 1.2. So it looks like the delta y and the dy are very close to each other and around 0.2. Does this confirm that? Yeah. dy is just slope times dx, which is 0.2. That's great. And remember, that's why the notation, there's this alternate notation for the slope of the tangent line, which is this slope goes by the name dy dx. Idealized change in y divided by change in x. Okay. So how to easily get this magic number m or dy dx or whatever we want to call it? Well, let's look at some other things we've already thought about. We actually have thought about a much more ambitious project, which is not just analyzing the slope of this curve at one point. It's the slope of, look at the slope of the curve at all points all at once. And that is creating what's called the derivative. Okay. And the notation for that is f prime of x. It's kind of attached in a weird way, though, but it's just f with a tick mark there. And so we know what that is. We know that it's creating a function whose graph has the property that the heights of this graph match the slopes of this graph. So for example, 0 slope, 0 height. 0 slope, 0 height. Positive slope, positive height. And in fact, if we believe our claim that this slope is 4, that should register as f prime of 2. The derivative of 2 should be exactly 4, which it looks like it's going. So this looks plausible in terms of the positive, 0, negative, and where it's bigger or smaller. Looks plausible to be the derivative graph. Also looks like a parabola, and we're going to determine that in fact it is a parabola. It is the graph of a quadratic. So the goal is, actually, what if we could get this whole function all at once? Not just get it point by point by point, laboriously with limits. Is there an easy way to get the whole thing? And that's what we're going to do in the next video.